to study, but there will also be tutorials, and I'm going to give you guys a list of practice problems that you guys can work, and that should help as far as that goes. And we'll go over some concepts on Friday. Hopefully, we'll have enough time on Friday. All right. Now, the practice problems will be listed in the book, but I will look and see which book has the best problems and that kind of thing. That's what I'm going to work on tomorrow, but I will let you know more about that on Friday. And the exam is postponed till Monday, just in case you didn't get the email yet. All right, so let's go ahead and get started. Where we left off on, what day is today? Where we left off on Monday is we had done redox reactions, we balanced equations, we balanced the half reactions, and we balanced the reactions that were done in acid. And that was, you separate the half reactions, so whatever's being reduced is in one, whatever's being oxidized is in the other. You assign oxidation states. One of them, you'll notice, has some oxygen on the reactant side, but not the product side. So then you add water on the right side, or it'll have oxygen on the reactant, but not the product side. So on the product side, you add water to balance the oxygen. And then you find out you have extra hydrogen on the product side, so you have to add H plus on the reactant side. And then that's good. And then, of course, you add the electrons or whatever. So today, I'm going to show you how to do it with a base. And then I'm going to talk to you about the activity series. So first, I've got a video. And then I'm going to work an example that goes slower, because I don't want you to be like, oh my gosh, that is like way too fast. So, yeah, I'll do an example of an acid and a base, but I'm just going to show you the base video right now. It'll probably remind you of some acid stuff, and then, we didn't get it on Monday. Didn't get what on Monday? Oh, didn't get it on Monday. Okay. Yeah, no, that's okay. Yeah, I'm going to review that today. No worries. Just have to find where it is. Okay, here we go. All right.
In this example, you'll learn how to... The problem reads, balance the equation occurring in basic solution. I minus aqueous plus MnO4 minus aqueous goes to I2 aqueous plus MnO2 solid. The balanced redox reactions occurring in basic solution follow the half reaction method of balancing, but add an extra step to neutralize the acid with the hydroxide ion.
So are you guys saying we did not get to the balancing the ones with acid on Monday, or I didn't get to the example on Monday? The example, okay. All right, I'll finish doing this one. I'm going to do an example of both of them.
The first step is to assign oxidation states to all of the atoms in the equation and identify what is being oxidized and what is being reduced. Begin with I minus. Since the charge is 1 minus, the oxidation state is -1. Then, for MnO4 minus, the oxidation state of oxygen is -2, and there are 4 of them. That's a total of -8. The ion has a charge of -1, so the manganese must have an oxidation state of +7. On the product side, the I2 is a free element and has no charge, and therefore has an oxidation state of 0. The oxidation state of the oxygen in MnO2 is -2, and there are 2 of them for a total of -4, which means the oxidation state of Mn must be +4. Notice that the iodine has increased in oxidation state from -1 to 0, so it's been oxidized. The manganese has decreased in oxidation state from +7 to +4, so it's been reduced. The next step is to separate the overall reaction into 2 half reactions, one for oxidation and one for reduction. The oxidation reaction is I minus going to I2. The reduction reaction is MnO4 minus going to MnO2. The third step is to balance each half reaction with respect to mass. First, balance all elements other than hydrogen and oxygen. For the oxidation half reaction, you have I minus goes to I2, so you need to add a 2 in front of I minus. The reduction reaction is already balanced with respect to all elements other than H and O, so you can continue on to the next step. Now, balance O by adding H2O. The oxidation reaction has no oxygen. The reduction reaction has 4 oxygen on the left side and 2 on the right, so add 2 water to the right. The next step is to balance H by adding H+. The oxidation reaction has no H. The reduction reaction has 4H on the right side, so add 4H+ to the left side. Now, neutralize H+ by adding enough OH- to neutralize each H+. Add the same number of OH- ions to each side of the equation. The reduction reaction has 4H+ on the left side, so add 4 OH- to both sides of the equation. Combine any H+ and OH- that occur on the same side of the equation to form water. The next step is to balance each half reaction with respect to charge by adding electrons to make the charge equal on both sides. Go ahead and try that yourself. How many electrons should you add to the left side of the reduction reaction to balance the charge? A, 2, B, 3, or C, 4? The correct answer is B, 3. The total charge on the product side is -4, and the total charge on the reactant side is -1. Adding 3 electrons to the reactant side makes the charge on the reactant side -4, which equals the charge on the product side. To balance the charge on the oxidation half reaction, add 2 electrons to the product side. Now, make the number of electrons in both half reactions equal. Do this by multiplying the oxidation half reaction by 3 and the reduction half reaction by 2. Notice that now you have 6 electrons lost in the oxidation and 6 electrons gained in the reduction. Add the 2 half reactions together. The 6 electrons on either sides of the half reactions cancel. The 4 H2O on the product side of the reduction reaction cancel with 4 of the 8 water molecules on the reactant side. The final step is to check that the equation is balanced by verifying that you have equal amounts of atoms of each of the reactants and products. Set up a table with the reactants on one side and products on the other. On the reactant side of the reaction, you have 6 I atoms. On the product side, you also have 6 I, so that balances. On the reactant side, you have 4 H2Os, which is 8 H. On the product side, you have 8 OHs, which is also 8 H. So you have 8 hydrogens on both sides. For the manganese, there are 2 on the reactant side and 2 on the product side. For oxygen, you have 4 from H2O and 8 from the 2 MnO4, which gives you 12 on the reactant side. On the product side, you have 4 from the 2 MnO2s plus 8 from the 8 OHs, which also gives you 12. Lastly, check the charge. The total charge must balance out on each side. On the reactant side, you have 6 I minus plus the 2 MnO4 minus. So the total charge on the reactant side is -8. On the product side, you just have the 8 OH minus, which is also -8 charge. So the charge is the same on both sides. The equation is balanced.
All right, so let's go over some of the examples. First, I'm going to go over, it's not that bad. It seems awful, but it's not that bad. So first we're going to go over a basic one. Then we're going to go over an acid one. Then we're going to go over, okay, let me make that more clear. We're going to go over an elementary example, meaning a simple example. That's what I meant by basic, but then I forgot about the fact that we're actually doing one in base, so that's just confusing. So first, an easy example. Second, an acid example. Third, an example of something in base. So I won't use the word a basic example because it's too, I guess you can't do that in chemistry. Yes, 3 types. Is somebody recording this? You don't want to say if somebody's recording it? Oh, okay. Colburn is recording it. Okay, cool. All right. So I'm going to do the examples that they had here in just a second. How do I undo that? Come on. No. Seriously. Stop.
In this example,
all right. Come on. Okay. Aluminum and copper. All right. All right, so we've got aluminum, solid, plus copper, 2 plus aqueous, making aluminum 3 plus aqueous plus copper solid. All right. Yeah, Colburn, if you could, can you let them know where to find the copy of the recording? All right. So the first thing that you do when you look at this is you want to look to see, okay, first we're going to give it oxidation states or oxidation numbers, all right? So we're going to use those oxidation rules that we went over last Friday. So aluminum is a solid, so there's a plain element, and it's not got a charge. So its oxidation number is 0. Now that doesn't work for molecules, just for elements, right? Over here, copper is an element, so it also gets a 0. Monatomic ions just get their charge. So copper 2 plus is a monatomic ion, so it's going to be plus 2. And aluminum is a monatomic ion, so that's plus 3. So now we want to check and make sure it's an oxidation reduction reaction. So we want to check and see whether or not the oxidation number changes when we go from one side to the other. And it does in both cases, because the aluminum is 0 on the left, but on the right it's plus 3. So that changed. And then on the left, copper is plus 2, but on the right it's 0. So then you want to separate them out. So aluminum, solid, going to aluminum plus 3. All right, and then we're going to do the same thing with the copper one. Yeah, no, that's no problem. All right, so step 1, give oxidation numbers. All right, using the rules. Step 2, separate the half reactions. That's what we're doing at this point right here. All right, so the next half reaction is going to be copper 2 plus aqueous goes to copper solid. All right. The next thing is we're going to check and see, is it acid or basic? All right. In this case, the answer is no. So since the answer is no, this is how we'll proceed. If the answer is yes, I'll show you one of those examples in a second. No. Balance electrons. All right. So to balance the electrons, we want both sides to have the same overall charge. So if you look at this one, at this side, no, not there. If you look at this side right here, it's neutral, but this side is +3. So we want to add electrons to the more positive side. So how many electrons would we have to add to make it neutral if we have good? 3 of them. All right. And then for the one below it, it's neutral on the side with copper solid, but it's got a charge on the side with copper 2+, a more positive charge. So we want to make both charges the same. So how many electrons do we add on the side with the copper? Good. Okay. The next thing you have to do is you have to make sure the number of electrons is the same by multiplying the equations. Okay. So on the top we have, well, in the aluminum half reaction, we have 3 electrons. In the copper half reaction, we have 2. So what we're going to do is we're going to multiply both of those equations by something so that they'll have the same number. So in this case, we can't multiply just one of the equations because you can't multiply something, a whole number by 3 and get 2, or a whole number by 2 and get 3. This is just not how math works, although sometimes my math works that way, as you've seen before. That's a little joke. I didn't say it was a good joke, though. Okay, let me move these things out of the way. All right. Let me put this kind of more where I want it. Okay, so we are going to take and multiply this whole thing by 2. Right? And we're going to take and multiply this whole thing by 3. And the goal here is just to make sure that the number of electrons is the same. So if I multiply aluminum 1 by 2, then I'll have 6 electrons. If I multiply the copper 1 by 3, then I'll have 6 electrons. So this is what we would get. We would get 2 aluminum solid, making 2 aluminum 3+ plus 6 electrons. And then for the copper one, we would get 6 electrons plus 3 copper 2+ aqueous makes 3 copper solid. All right. And then you want to look and make sure you have the same number of aluminums on both sides and the same number of coppers on both sides and so forth. I have 2 aluminum on the left. I have 2 aluminum on the right. I have 3 copper on the left. I have 3 copper on the right. So I'm good. The next step is to add them together. That's a good question. All right. So the one that's oxidized lost electrons. So losing electrons is oxidizing. So the one that lost electrons was aluminum, so that was oxidized. And the one that gained electrons was reduced. All right? So when we add these two together, we have to get rid of anything that's on the product side that's also on the reactant side. Are we looking at charge or oxidation number? Oxidation number. That's a good question. The oxidation number. Correct. We're looking at the oxidation number. All right. So I noticed that I have 6 electrons on the reactant side and 6 on the product side. Correct. It went from 0 to +3. And you see that it lost electrons because these electrons were inside the aluminum before, causing it to be neutral. And then it fell apart, lost some of the electrons, and became Al3+, and these electrons are moving away. They're going off to be on their own. Actually, they're going off to be with copper. And in the case of copper, copper's 2+, but to become copper solid, it has to gain electrons to become copper solid. So what you're looking at is what happens when it gets to the product side. It doesn't have to, do you mean in the same half reaction? No. So in this case, I have 2 aluminum solid, 2 aluminum 3+, and 6 electrons. And I'm going to cancel those 6 electrons with the 6 electrons from the copper. If I add, that's just a shortcut, because if I add these all together, on the left of the arrow, I would get 2 aluminum plus 6 electrons plus 3 copper 2. And then I'd have the arrow. And then on the right of that, I'd have 6 electrons, 2 aluminum 3+, and 3 copper. So then I would have 6 electrons on both sides, and I would cancel them. So the only reason I'm canceling them here is just as a shortcut. They have to tell you it's a base or an acid. That's a good question. Right, so the final answer is this. Hang on 1 second and I'll look at those comments. All right. Okay, so I don't understand step 5. What happens to the electrons you added in the previous step and how are they balanced? And okay, so what happens, what you're doing is you're looking at the number of electrons here and here. And we can see those are not the same number of electrons. So if they're not the same number of electrons, what I'm saying is aluminum lost 3 electrons, 2 of the electrons were given to copper, and 1 was obliterated. That doesn't actually happen. So if I have 3 that are given away, 3 must be gained by something else, right? So in this case, since we know that 2+ has to be balanced with 2 electrons, if we multiply the whole equation by 2 for aluminum and 3 for copper, when we do that, the whole purpose is so that aluminum will be losing 6 and then copper will be gaining 6. So that part is balanced. Is that better? No, that's okay. All right. So that's all you have to do with the plain ones, the simple ones. This one was simple. It was not acid. It was not base. You could consider this just being in water. Just standard oxidation reduction. All right. Anybody need to take a picture of this or anything before I go on to the next one? Sure. Okay. So how this one's balanced, first you take it, you give it oxidation numbers like we did up here. Then you separate it into half reactions like we did here and here. The aluminum was +3, so I had to add 3 negatives, and that would be 3 electrons. The copper was +2, so I had to give it 2 electrons. And then I have to multiply them so that both sides have the same number of electrons. So 3 times 2 is 6. So that gives me these 6 electrons. And then 3 times 2 is 6 again. So that gives me these 6 electrons. But we can't just multiply the electrons. We have to multiply the entire thing. So that's why we've got 2 here and here. All right. So that's how we balance them. It looks a little funny because we haven't had identical coefficients in the past, but we will have them now because we're balancing the whole thing, including charge now. All right, what's your question?
Why did we use the oxidation reduction method? Why didn't we just did all of it in the equation?
The reason is because it's an oxidation reduction reaction, so it has to have the electrons balanced. Up until this point, we've only been concerned with balancing just general, simple examples. 13 minutes left. Oh no! Okay, so we've only been balancing simple equations. So now we're just showing you what to do with a little bit more complicated example of balancing. All right, so let me show you, you're welcome, let me show you an acid example. And I'm probably going to do the same one they did. All right, so it's me iron and MnO4 minus. Let's see. 2 plus. All right. All right. So this is the acid example. So I'm going to put acid at the top. All right. They would have to tell you it's an acid. If I don't get to the OH1 today, I will do the OH1 on Friday because that's pretty much the last thing I've got on this. So with this one, you do the same thing. You're going to give it oxidation numbers using the oxidation rules. So this has, the iron is a neutral atom. It's just in its elemental form, so its oxidation number is 0. There are no other things in elemental form. They do have 2 monatomic ions, so they would just get their charge. And then MnO4, manganese is not a polyatomic ion. Manganese is a transition metal. There are no rules for transition metals. There's a rule for oxygen. So we're going to assign oxygen, unless it's a peroxide, it's going to be -2. So then we're going to do a formula to figure out what manganese is. So Mn plus 4 times whatever oxygen is equals the charge, and MnO4 minus has a -1 charge right there, so that's where this number comes from. All right, so then that becomes Mn plus 4 times -2, because -2 was the charge we gave it. That becomes Mn minus 8 equals -1. I'm going to add 8 to both sides. Mn equals +7. Let's see, where did the -2 come from? So the -2, that's for the oxygen. That was the oxidation state for oxygen. That's a good question. Okay, so the oxidation number for manganese we calculated to be +7. Now we're going to look and see what changed. So manganese goes from +7 to +2, so it changed. And oxygen, you can see, is like nowhere to be found, right? And I'll explain that in a second. Iron goes from 0 to +3. The reason oxygen can't be found is because this is an acid and we have to put it's there, but we have to show it in the equation. And I'm going to show you how to get that taken care of here in just a second. All right. So we're going to separate them into half reactions just like normal. All right, and the other one. All right. Now we want to balance that nasty oxygen. I have oxygen on the left. If you have oxygen somewhere, but you don't have it balanced, wherever you have less, you're going to add water to balance it out. In this case, I have oxygen on the left, so I'm going to add water on the right to balance that oxygen. And since I have 4 oxygen, I have to add 4 water because each water has 1 oxygen in it. So now I have 4 oxygen on the left and 4 oxygen on the right. Problem is, I now have 8 hydrogen on the right. So I'm going to add hydrogen to the left in the form of H+. All right, so it's H+ plus MnO4- makes Mn2+ plus 4H2O. Now, H+ has an oxidation state of +1, oxygen of -2. On the right-hand side, hydrogen still has a +1 oxidation state and -2 for the oxygen. Those don't change. The only thing changing here is manganese. So we're going to look and see, remind ourselves of what the oxidation state for manganese was. +7 there, and this one was +2. So on the left, it's way more positive. So I've got to add electrons so it equals the right-hand side. The right is +2. The left is +7. What would I do? So the reason the hydrogen was added was because when you add water, there's hydrogen there. So we have to make sure that we have hydrogen on this side. Right? Yes, so it's about correct. So we're going to add 5 electrons to this side. And that would cause this to end up being just a +2 charge. Right? So then we have, kind of running out of room. I'm going to put the electrons here. Right? On the top, I've got 3+ on the right and neutral on the left. So I'm going to have to add some electrons on the right. All right? That's good, but I have 3 electrons on the iron one and 5 electrons in the manganese one. So I'm going to multiply my equations. I'm going to multiply this one by 5. And this one by 3. So that's going to give me this 5 Fe solid makes 5 Fe3 plus aqueous plus 15 electrons. And the other one is going to become 24H plus aqueous plus 3 MnO4 minus plus 15 electrons makes 3 Mn2 plus aqueous plus 12 H2O liquid. Okay. Now we're going to add them together. Looking at the right side of both arrows, I see I have 15 electrons there. Looking at the left side of both arrows, I had 15 electrons on the left-hand side. I'm going to cancel those. Now I'm just going to write down everything that's left. Come on. All right. And that's the answer for the ASP one. So the only thing different in balancing it, the only thing different is that one side will have oxygen and the other side doesn't. Then you're going to add water. Then you're going to add hydrogen. All right. So you balance it just like the simple ones. Only difference is that oxygen. The reason I added 5 electrons on the reactant side, or are you talking about right here? Is that what you mean, Samantha? For the MnO4 portion. Oh, okay. The reason I added 5 electrons there. That's because manganese was +7 here, but it's +2 on this side, and we want it to equal the same thing. Now, they don't have to always go neutral. They just have to both have the same charge on both sides. So if this side is +7 and we add 5 electrons to it, then 5 of those pluses will cancel and leave us only 2 pluses. So then on the left we'll have 2 plus, and on the right we'll have 2 plus. You're welcome. The reason I put 4 for the oxygen, for the water, was because I have 4 oxygen over here. So I'm putting 4 water to get those 4 oxygen. On the left. You couldn't, and the reason you couldn't is because if you put 12 H2O on the left, our oxygen would still not be balanced, and it wouldn't indicate that it's in an acid. It would indicate that it was in an aqueous solution. So we put the H plus there because it's in an acid solution, and this is just showing that we have acid in there. The only thing else we would do if we had a base was we would neutralize the H plus with some OH. But we're not going to get into that until Friday. They have to tell you it's in an acid solution, otherwise you would not know. In the lab, you'd know it's in an acid solution because you would have put it in an acid solution, or you could test the pH using a pH meter. I'm gonna have to think about it actually, because I'm gonna have to go back and think about all the stuff that we studied. But I will tell you tomorrow. I'll post it on D2L sometime tomorrow. Cool. Yeah, I would have sat there trying to figure it out too, Carson. I would have done the exact same thing. That just shows that you are really bright. So that is really good. You think, which is excellent, especially in science. Well, I mean, it's good. It doesn't really matter what you do. You have to think. Like even if you're a waitress and you're not thinking about it, because I used to be a waitress, and if you don't think about what you're doing, then you'll be giving people the wrong food and forgetting to enter in their food. Not that you don't do that even when you do think, but that does happen on occasion. Glad I'm not a waitress anymore. That was really hard work. Well, that was kind of fun. I did like meeting new people every day. All right. Well, I will talk to you guys on Friday, and I'll send you some information tomorrow. No, it should be the stuff that we've learned, right? So be going over the ACS exam booklet. Once you've done it, do it again. Do it again, do it again, do it again, until you take the final exam. Just go through the book over and over. When you get to a place where you're stumped, go to YouTube or go to some of the tutorials I've posted on D2L and see if you can figure it out. So hopefully you can there. May 3rd. That's Monday, right? How many other exams do you have? If you have 2 other exams, I think I have to change it. But if it's just 1, I think you have to take both of them. Just 1. What time is your first exam on Monday?